Hello, repair time again. This time I have Anritsu MG3670B signal generator. It was sitting here for quite some time waiting for its turn, and when I initially checked it, when I got it, it had no RF output. But now it seems to have some other problem. Let's turn it on. So it boots up with all self-tests passing, and by the way, the screen flickering appears on the recording only. I see it as nice and steady, no problem at all. So it boots up and it does not respond to front panel controls at all. And it did respond before, so it seems like we have more than one problem. And unfortunately I couldn't find any service manual for this thing, so we will have to manage without. So let's take it apart and see what can we do. Here is the back of the unit. By the way, this thing is quite heavy. There is a sticker here, caution, heavy weight 18 kilograms. So we have a couple of fans, some outputs, burst trigger input, GPIB. This is a 10 MHz reference, output and link to the input, so the link can be removed to use an external reference. Here we have some link between input and output of a local 1.5 GHz oscillator. This is a sticker, Anritsu Corp, made in Japan, serial number and options 03 and 25. Option 3 I believe is high stability time base. I'm not sure what option 25 is. And this is a list of extensions. It seems like this thing should have 3 modules installed. So I removed the covers, and removing the top cover did not help much. There are more internal covers. Everything is thoroughly shielded, and that's why this thing is so heavy. Removing the side cover did not help as well, and the same thing on the other side. So let's look at the bottom. Here is the bottom of the unit. And this seems to be the main distribution board with some connectors for the modules, and on this side as well, and some power distribution as well. This board is marked DC to DC regulator with a bunch of test points with voltages marked on the board. Very nice. This is a separate board called filter board. There is another one here also called filter board. This is some sort of RF module, and there is a small PCB here called divider filter, so maybe this is some sort of a divider. So I already checked the voltages here, and they are very close to the specified values, no problem here. I managed to take the front panel out. Not sure this was useful, but let's have a look anyway. So here we have a sharp LCD made in Japan, and this is the control panel. And maybe you can see here there are 2 boards, one on top of the other. I removed some covers here, and check this out. We have very serious RF plumbing going on here. 4 massive fully shielded modules, and one more module here. Two boards are visible, and a smaller shielded RF can on this side. This must be the 10 MHz reference. We've seen connectors on the back. There is a smaller RF box here. Under this cover, I believe we have the main computer. This is GPIB. I see configuration switches, LEDs, and batteries to retain some configuration, I suppose. And I did not open these covers yet. Too many cables going to the front panel and the back panel. These three boards are marked modulation unit, filter unit, and modulation unit as well. And this is a power supply. Here is a strange indicator on the power supply. I have no idea what this is. Here is the CPU board. There are 4 batteries here for some reason. I measured them, they are fine, 3 volts, no problem at all. This is the main CPU, Toshiba TMP68HC000T, 12 MHz. The software is revision 1.18. The date codes on the chips are from the year 1995 and 96. And let's have a look on the other side. Some more logic here. This is a CDMA modulation board 1. So we have a shielded RF can, 5 Xilinx FPGAs, 4 Texas Instruments DSPs, and a bunch of memory. And there is a lot of flux around the memory chips, as if they were replaced at some point. And also a lot of modifications all over the board. And on this side as well. Here and here, and the wire here. This board is marked CDMA Modulation Unit 2. And on this side it is marked Filter Unit. And we have, I believe, more DSPs here, and this chip is also DSP by Texas Instruments. Some other logic and bunch of software, some configuration switches here. Probably a test point or something. And this is the third board, marked here pi/4, the QPSK modulation unit. And here we have a couple of Anritsu branded chips, a lot of other logic, some configuration switches here, and some more software. Check this out. It occurred to me to start this thing without the modulation boards. And here we go. We have a responding front panel. My guess is that something is wrong with one of the modulation boards, so that main CPU could not initialize it and kept trying forever or something like that. So I think now it's time to check some basic functionality. I started checking. This is connected to the reference output on the back of the unit through 6 dB attenuator here, and no problem at all. The 10 MHz reference is fine. So let's disconnect this and connect the output. Here I have set 10 MHz as well, 0 dBm. The RF output is on, and we see nothing at all. And I checked on different frequencies, and there is nothing. And this is the LO from the back of the unit. I removed this link we have seen before, and no problem at all, we have 1.5 gigahertz. They say it should be minus 13 dBm, and we read minus 6 dBm here. So it's a bit higher, but I would think it's not a problem. Let's have a closer look inside. I believe this little module is the main oscillator, so-called YIG or YIG oscillator, which can be tuned in a wide range of frequencies. In case of this instrument, the range should be about 2.25 gigahertz. But the lowest frequency of this oscillator is certainly not the lowest frequency of this instrument, which is 300 kilohertz. Perhaps the lowest frequency of this guy is several gigahertz, and at some point here this high frequency should be down converted to the final frequency range of this generator, which is from 300 kilohertz to 2.25 gigahertz. So let's check this thing. Disconnect this rigid coax, connect spectrum analyzer, and have a look. I really hope it works, otherwise I don't like my chances. These things are either not available at all or too expensive, and this can easily mean that this instrument is beyond economical repair. Look at this, we have a tone here, and the signal is quite strong. We have 6 dB attenuator here, and the signal is just above 0 dBm, and we have 5.392 gigahertz, which is the lowest frequency because I set the generator to 300 kilohertz. Now let's set the highest, which is 2250 megahertz, and now we have a tone here which is 7.627 gigahertz, and the difference is about 2.25 gigahertz. Very cool. I was not sure what frequency range to expect, but this looks fine to me. I'm quite happy that the YIG oscillator is alive. So the oscillator seems to be alive. I connected this rigid coax back, and it goes into this module here. So it seems that this module is to control the YIG oscillator, and this must be the output from it. So let's check it. I connected the spectrum analyzer here, and essentially I see the same tones, but about 10 dB lower. Now we are looking at the high end of the frequency range. I'm not sure what to expect here. Most probably this is fine. So we have signal at this point, and unfortunately I don't understand yet what's going on here. Lots of connections going every which way, and I don't even have a block diagram. So let's try stepping back from the output. I managed to remove the side panel. Here it is. After removing a few screws, it slides right out. So here is the output connector on the front, and I see a rigid coax running to this point, and this must be the output attenuator. So let's try checking here just before the attenuator. I see absolutely nothing at this point. So the attenuator is connected to this module, and the only rigid cogs besides that is this. There is one more flexible coax here, must be a lower frequency one. So let's check here. So at this point we have about minus 20 dBm, and there is no attenuator now, so this seems a bit low. And this is at the high end of the frequency range. And look what happens if we go to the low end. I will set 300 kilohertz here. And we are down to minus 36 dBm. Let's increase the frequency a little, let's say 100 megahertz. And now we have about minus 30. And let's try somewhere in the middle, like 1 gigahertz. And here we have minus 14. I would expect approximately the same level across the whole frequency range, plus minus a few dB or something like that. And of course I checked my connections and tried a different cable, and there is no difference. So I think something is wrong, and I'm not sure what to do next. Let me think about it. Here I removed the last two modules to try to get more understanding what's going on here. This one is the final module with the output, and this one is just before it, and it's called converter filter here. This must be the input to it, because that rigid coax from the YIG controller was connected here. And this must be the output, because it was connected to this module. Let's start from this final module. I already removed the screws. Here we are. So the input is here, coming from the other side of the module. Then signal goes through this box, and then through this box, and finally into this box. And now it seems to me that these two things are the step attenuators, and this must be for reverse power protection or something like that. This is the other side. Again, I already removed the screws. And we have an RF amp here. This is the input. This is the output going through to the other side we have seen before. And if we have a closer look at the input, here is some passive filter, two amplification stages, there are two small active devices, and then signal goes through this chip. I looked it up. This is 15 dB digital attenuator in 1 dB steps, and the bandwidth of this guy is 0 to 2 gigahertz. So they are using it slightly out of spec, stretching it to 2.25 gigahertz. But my point is that there is no down conversion here at all. The input should be already down converted. And we already checked the input, and we saw that 5 to 7 gigahertz signal with low amplitude dropping towards the low frequencies. So that was clearly wrong. It seems like that down conversion is not working properly, and we see some sort of feed through. This is the converter module, and again I already removed the screws, and I also removed the screws from these two shields so we can have a better look. These two are identical mixers by ST Microwave. and the covers are loose. Let's remove them so they don't fall out when we start turning this module around. There you go. So this is our RF input, again from about 5.4 to about 7.6 gigahertz. Here it says drive amp on the board. So the signal is amplified and it goes out right here. Here it is. It goes through this filter, which says 5.4 to 8.6 gigahertz, and comes back. Which is this point, and it goes into the low input for some reason of this mixer, and this is the IF output. So this must be the final result, and this port was connected to the output amplifier, and we saw incorrect results here. So now let's look at this. It says on the board 4.2 gigahertz PLL. So this input must be some sort of a reference. So it goes here, and this thing is 4.2 gigahertz oscillator. Apparently can be mechanically adjusted. So the result goes right here, gets amplified, and there is a splitter here. So half of the signal, I would think, goes this way, gets amplified, and closes the PLL loop. And I think this pin is tuning, because I see it goes out right here and is connected to this pin of the oscillator. This pin. So it must be tuning. Another part of this 4.2 gig signal goes this way, gets amplified, filtered, and goes into the LO input of this mixer. And here things get a little weird, because apparently this RF input is used as output, and this IF output as input. And I believe so because I looked up this amplifier chip. There are many of them on the board. This is NEC amplifier, and this is the input, this is the output, so the signal must go this way through this mechanically adjusted filter, and it goes out here, goes through this filter, which is not marked at all, and comes back right here, which is this point, and it goes into the RF input of this mixer. So apparently LO and RF are swapped. And let's see, what does it take to convert 5.4 to 7.6 gigahertz signal into the final result, which should be from 0 to 2.25 gig. Apparently we need to subtract approximately 5.4 gigahertz. And here we are. Here it says 5.4 gig amp on the board. So it seems to me that this LO 4.2 gigahertz LO is mixed with something else and becomes 5.4 gigahertz here. So this input must be about 1.2 gigahertz. So all this kind of makes sense, except some liberties taken with swapping pins of the mixers, especially this one. But I assume that Anritsu engineers know what they are doing. So now we need to understand what's wrong here. And now I put this converter module back in, and I'm checking at this point. I removed this link between this port and this external filter, which goes into the final mixer, and we should see 5.4 gigahertz allow here for the final mixer, and there's absolutely nothing there. And of course the final conversion is not going to work without it. This is the next module. I removed the screws here as well. Let's see. Here we have a modulation board, and I think these two are modulation inputs, and this is some sort of a heated chamber. Let's see if I can remove this. There you go. Here we have 1 ohm power resistors for heating, and let's see, this must be the reference input, and at this point it must be 100 megahertz, because these two are 100 megahertz crystal filters. And here is the reference output, and this goes to the converter module. And also the reference must participate in this modulation process somehow. And I see several connections to the other side, like here and here. So let's have a look. I already removed the cover here. This is a 1.5 gigahertz generator. This is the output. This goes to the back panel. And there is a jumper, and it comes back here. And this must be modulation, and they combine here somehow, and at this point we must have 1.2 gigahertz, because these three are narrow filters marked 1200. And this must be the modulated 1.2 gigahertz signal, which goes to one of the mixers in the converter module. And let's see if I can remove this one as well. There you go, and essentially the same thing. 4 power resistors to heat up some chamber. This is the reference output from the modulation board that goes to the converter board. So we see 100 megahertz and around 7 dBm. This looks excellent. And this is the 1.2 gigahertz output from the modulation board. The frequency is perfect, but the amplitude looks a bit low. It is about minus 20 dBm. And this is one of the inputs to a mixer. And I would expect something higher than this. Let's say something closer to 0 dBm. Here is the converter module again. Let's summarize what do we know so far. We know that the input signal here is fine, the reference is fine, and the output is bad. Essentially, we see a weak signal from the input leaking through, and there is no 5.4 gigahertz allow at this point. We measured at this point, and there is nothing at all here, and this must be a result of mixing here, going through this filter and this amplifier. And we also know that this signal, 1.2 gigahertz, is present, but the amplitude seems to be low. So we need some way to start checking around here. The problem might be because of this low input here, or maybe this 4.2 gigahertz signal is missing. Let's say this oscillator might be not working, or some amplifiers here not working, or maybe this mixer is bad. So I noticed this screw here covering a hole right there. So I'm thinking about passing a thin coax through this hole and attaching here to the output from the mixer, so we can check here by passing this filter and this amplifier. Let's try. Here we are. I passed this coax through this hole, attached the ground here, attached the signal here, and I know this is far from perfect, because all the distances here, let's say this trace going nowhere, and this one, and this weird shape here, they are all important, and the distances between them and the ground and between each other are important. And I introduced more ground here, and extra load at this point certainly disturbs some matching, but we need some visibility into the problem, and I'm hoping that we will learn more than we know now. And here is what we've got at that point. We are looking at the frequency range from 0 to 6 gigahertz, and there is nothing at all here except this tiny blip around 300 megahertz and about minus 57 dBm or so. I don't see that 1.2 gigahertz low feed through. Perhaps it is below the noise floor. It was about minus 20 dBm to begin with, but still I would imagine it should stick out a little bit. And there is no 4.2 gigahertz feed through as well, and no intermodulation products. Now I moved this test cable from this point to this point before the mixer and even before this filter on the board, to see what's going on here with the 4.2 gigahertz input to the mixer. And to pass this cable here, I removed this shield again from the mixer and attached the cover of the mixer with a couple of screws. So let's put the cover back and have a look. We are looking at the range from 3 to 5 gigahertz, and there is nothing here at all. And now I removed this shield between sections here and passed this cable all the way to the output from the oscillator. I'm so glad these removable dividers exist here, so we can check what's going on here with closed cover. Let's go. And check this out. Here we do have around minus 17 dBm and about 4.2 gigahertz signal. 4.187, but the resolution now is so crude. We are looking at the range from 3 to 5 gigahertz. Let me zoom in to have a better measurement. Here we are. Now we have 100 megahertz span, and we can see that the frequency is almost exactly 4.2, but it's not stable. It's shifting up and down a little bit. I think something is wrong with PLL. And now I set the span to 10 megahertz, and we can clearly see that the frequency is shifting. And now we are looking at the oscillator tuning pin here on the scope. We have 10 volts per division, so the top of this waveform is around 12 volts, which is one of the power rails of the oscillator. So it seems to me that the PLL is trying to pull the frequency and is hitting the power rail for some reason, and the frequency is about 8.5 Hertz. So something seems to be wrong with PLL. Now I remembered seeing this jumper here, which I did not mention. I did mention, I believe, that this pin seems to be the output from PLL that goes to that tuning pin of the oscillator, but not directly. It goes through this jumper, and if we move the jumper, then the PLL is disconnected and the tuning pin is connected to some fixed voltage. So this must be for testing. Let's try. So I moved the jumper, and sure enough the frequency looks stable now. I set the span to 1 MHz and we don't see any movement, and the frequency is 4.197915, which is slightly more than 2 kHz off, and I'm not sure if it's close enough or not. Maybe PLL is asked to pull too far, and that's why it is hitting the rail. If so, then we need to adjust the frequency of the oscillator. So we might have more than one problem here. Before worrying about the frequency, I would like to find out why there is no signal at this point. Perhaps one of these amplifiers is dead. So let's try to move this test cable, let's say after the first amplifier, and see if there is signal at that point. I moved the cable to this point after the first amplifier, and let's also check the power rails here. I see that these two amplifiers receive power from the same power rail, which is this pin. So we should see this pin on the other side. It's marked LND8, and the power goes through this filter, and then there are two inductors, one for this amplifier and one for this one. So let's check what we have here. Look at this. We have two very low amplitude tones at this point. This one is about 4.33 GHz and about minus 45 dBm or so, and the other one is about 4.2 GHz and slightly lower. So this one seems to be the oscillator, and this one might be, I guess, an intermodulation product with the reference, because it is about 100 MHz higher, which is the frequency of the reference. And the frequency measurement now is not very precise at this resolution. We have 500 MHz span. So something seems to be very wrong here. Perhaps this amplifier is dead or something like that. And the PLL might be fine or not, but it seems like the signal does not even reach the PLL. And now let's check the power. Here's our ground, and this is the power pin. And there is our problem, 0.2 volts. Here on the other side of the board is a regulator, and these three pins are the regulator pins. This must be the input, 12.5, and this is the output, 0.2 volts. So either this regulator is dead or the amplifier is overloading it. So I desoldered this wire from the pin, and here we have the voltage from the regulator. which is a little bit too low. Here is another amplifier in the 5.4 GHz path. So I'm still not sure what's wrong here, regulator or the amplifier. One way is to try loading this regulator, but we need to know the current. And another way is to inject a voltage into the amplifier from a lab supply, but we also need to know a sensible current limit. Let's see if I can find a datasheet for this amplifier. I found a datasheet. This is a 2 to 8 GHz wideband amplifier, about 15 dB gain. And here we have a supply current. Typical is 135 milliamps, and 180 is the maximum. And seems like 8 volts is the typical supply voltage. And now I'm providing the 8 volt rail from this lab supply. I set the current limit to 400 milliamps just in case. And we can see that the actual current is 244, almost 245 milliamps, or about 122 each amplifier, which is even slightly less than the typical 135 according to the datasheet. So there is no problem here, no overload. Let's check the RF signal. Yes, the signal is nice and strong. This is after the first amplifier, around 0 dBm. No problem at all. Now we need to fix the voltage regulator. And now I'm checking this voltage regulator using this electronic load, and it puts out 8 volts. Let's try to load it with 100 milliamps for now. And there is no problem at all. Let's increase to 200, 300. No problem. I'm not sure what was wrong with it before. Let's have a look. Here is this voltage regulator. Perhaps you can see it. And I let it run under the 300 milliamp load for quite some time, and there was no problem at all. So I'm starting to suspect, maybe you can see some sort of contamination on the board all around this place. And there is ground plane around this point of connection of this little wire. So maybe there was some short somewhere and I somehow removed it during soldering. I'm not sure what's going on here. I'm tempted to clean the board all over this area and solder the wire back and try again. So I cleaned the board, soldered that wire back to the pin, and there is no problem with the power rail now. So I moved that PLL jumper into the working position, and we have nice and stable signal now, 4.2 GHz exactly, with 500 kHz span. And the tuning voltage is also nice and stable, sitting around 4 volts. This looks excellent. I just found that this 1.2 GHz signal at this port, which we looked at before, and it was low, about minus 21 dBm or so. I found that it was low because I did not connect these two modulation input signals. And it turns out this is important for some sort of mixing process here in this module. When this 100 MHz reference signal is tripled and mixed with the 1.5 GHz allow, and the result is this 1.2 GHz output with some sort of modulation riding on top of it. And even if we are not really modulating anything, I guess there are some carriers present anyway, and they are important to have in this mixing process. Here is what we have at that port with the modulation signals properly connected, about -3 dBm, and with some loss in this long and not very good cable. So this looks much better. And now we are back to the converter module. I removed the test cable, and now we are looking at this port, which is 5.4 GHz LO output. Just before it should go through that external filter, which we don't see because of the frame, into the final mixer. And here's what we got. Nice and strong -10 dBm signal. And I'm not entirely sure what level we should expect, but this does not look bad at all. So let's put this link back in place and check the result of the final down conversion. This is the output from the converter module, and the frequency is set to the maximum, which is 2.25 GHz. And the frequency is not quite right, 2.2288 something, and this analyzer has a very good reference, so this is suspicious. Perhaps some adjustment is needed. And the level is about -24 dBm, and I'm not sure if this is correct or not, so let's try with the output amplifier module in place. So now with the output amplifier in place, we have the right output level here on the front panel output. We have 0 dBm set here, and we are reading -1 dBm here, and I can easily imagine 1 dB of loss in this cable and 2 adapters. So this is great, and we can try changing the level here, let's say to -10. -11 here, let's go to -20, -21, -30, -31. Perfect. Let's go back to 0. So the level is right, but the frequency is quite a bit off. I set exactly 2 GHz here, but here we have 197,875, which is quite a bit off, and this analyzer has a very good reference, so this is incorrect. And look what happens if I change this frequency just by 1 Hz down. It jumped up, and quite a bit. We have a span of 50 MHz here, so it jumped by probably tens of megahertz. And if I keep going down, it does not jump like that anymore. But if I set 2 GHz again, it jumps down again. So something is not right with the frequency control. Perhaps with the EGA oscillator control module. Here we have 2 more modules we never looked at before. Let's start with this one. It is marked RF Cont 1 on this side and RF Cont 2 on this side. There are 2 boards, and this probably means RF controller or something like that. This connector is for EGA oscillator coils. This is input from EGA oscillator, and this is output to the converter module. This goes to this module, and here's a cable here that goes back and connects here. And let's see, this one is marked local board 1 here and local board 2 on this side. also two boards, almost fully shielded. This is the input from reference, and this goes out to the reference input of the converter module. So let's see if we can understand what's going on here. So I removed this cover here, and there is one more cover, and it was stuck, and when I managed to carefully lift it, here is what I found. This RF absorber somehow deteriorated, and a piece of it is stuck to the board next to the amplifier chip. And I wonder, how did this happen? Could it deteriorate by itself, or this is a sign of overheating? Anyway, let's have a look what's going on here. So this is the input from EEG oscillator. Then I see a splitter here, and one part of the signal goes out, and this goes to the converter module, and another part goes to the amplifier. This is called isolation amp here on the board. So the signal is amplified, filtered here, and goes to the other side. Here is the other side. I already removed the covers. This board is called sampler, and at this point that signal from the isolation amp comes in. It goes here, and this looks like a mixer. So this must be another input to the mixer coming from the other module called local board. The result goes here. This is an amplifier. And this Motorola chip is a phase detector, specifically made for precision phase lock loops. There is some adjustment here. This was covered as well with this little cover. This is a 12-bit Burr Brown DAC, and these four are identical Anritsu branded chips. I'm not sure what they do. I found a service manual for MG3670X line of signal generators. They can go up to 20 GHz. So this block diagram looks quite different, of course. But I believe this part looks very similar. And this is EEG oscillator control. So it can be very helpful to understand better what's going on. Here is the description and the block diagram of that part. So let's rotate it and have a look. There are several phase lock loops here. One loop is this reference loop to produce 100 MHz from 10 MHz reference. This is EEG oscillator, and I believe this part looks a bit different in our case. We have seen that the EEG oscillator output comes in, gets split right away, and one part goes right out to the down converter module. And the other part goes through the isolation amplifier and into the sampler. And the other input into the sampler is from this coarse loop, and it goes through this step recovery diode here to produce a lot of harmonics. So the idea here is to program from the main CPU this divider in the coarse loop, so that the resulting frequency would have one of the harmonics quite close to the desired frequency. So after mixing with this EEG oscillator signal here, the result would be in this range from 21.5 to 40 MHz. So this result goes into this phase detector, and it is compared with this signal, which comes from this fine tuning loop. which is also programmed from the main CPU to produce fine-tuned frequency, which is compared here, and the difference should drive the fine-tuned coil in the EEG oscillator. And these frequencies in our case can be a bit different, but the overall idea should be the same. So this input into the sampler must be from the coarse loop, and this input must be from the fine loop, and here we should see the output from the sampler. I have this BNC adapter which should fit these connectors, and we can solder a cable at this point. Let's check what's going on here. This is the input to the sampler, about 97 MHz and a lot of harmonics. This looks quite good. And this must be the fine-tuning signal, about 12.5 MHz, and also with a lot of harmonics. And I'm not sure harmonics here are intentional, but I think this looks good as well. And this is the output from the mixer and the sampler. The amplitude is low, minus 36 dBm or so, and the frequency is different, about 13 MHz. And I connected the signals back, so the phase lock loop should be locked, but apparently it is not, so something is wrong here. I took a closer look at this board, and in particular under this little cover, and I think I see something that I didn't notice before. This capacitor, which is mounted horizontally for some reason, I believe has some corrosion on the legs, and it seems to me there is some residue on the board around it. Let's check this capacitor with the LCR meter. Capacitance mode 1 kHz. Let's enable ESR as the second parameter. This is a 10 microfarad 35 volt capacitor. 1.8 microfarad 40 ohm ESR. This looks quite bad. So let's desolder it and check out of circuit. Sometimes it can be misleading in circuit. It looks even worse out of circuit. 700 nanofarad and about 78 ohm ESR. And it might be not just because it is out of circuit, but because it was heated up during desoldering and more electrolyte evaporated or something like that. And it doesn't matter. Clearly this capacitor is dead. I installed a new capacitor and look at this. This is the output from the RF control module, which should go to the down converter module. I didn't want to install that and connect all the plumbing just yet. And we have exactly 7.4 GHz here, as expected given 2 GHz here. And now let's see what happens if I adjust this by 1 Hz down as before, and back, and down again, and back. You see, this frequency jumps briefly and comes right back. And I think this is because the coarse loop frequency is reprogrammed at this point, and the fine loop is adjusted accordingly, of course. And the frequency is unstable for a brief moment until the PLL locks again. And this is normal given this architecture with coarse and fine loops. We must have multiple such points along the frequency range of this generator. And now let's try changing this frequency. Let's see, we have 10 megahertz span here, so 1 megahertz per division. So let's go down by 1 megahertz, 1.999. There you go, it jumped exactly 1 division. Let's see, and let's enable the counter to get exact frequency, 7.399 exactly. So this looks perfect. And now with the down converter module back in place and the output from the front panel, maximum frequency 2.25 gigahertz. The level is correct, the frequency is correct as well. And let's try changing the frequency by 1 megahertz, which is 1 division, 2.249 gigahertz. And yes, it jumped by 1 division exactly. Let's see, 2.249 gigahertz. Looks great. So everything is back together here, but I didn't worry about the options yet. This video is getting too long. Maybe I'll make another video troubleshooting the options. If you like this one, give it thumbs up. Thank you very much. Bye.